Hi, everyone. This is the last lecture, and we're here at the end of the semester. But looking at the clock, it says I'm at 39 minutes, so maybe I have 20 to 40 minutes left to finish the lecture. I won't take that long, but first, I just want to say I think you guys have done a pretty awesome job this semester. I think these circumstances have been extraordinarily difficult, and uh, and I'm kind of amazed by how everyone has kept up and took all their quizzes and their midterm, and now are going to take a final and actually learn exactly what students learn every year in this course. But in your case, given the circumstances, it's a lot more impressive. So the syllabus says this course ends with chapter 9, but in fact, there's kind of one core topic that we've left out, which is kind of cementing this idea that probabilities have something to do with relative frequencies. So we have about 15 more minutes here that I'd like to talk to you and explain this little tidbit from chapter 10 that'll kind of go full circle on our course to the first lecture when we said, well, probabilities are these abstract things. They're something that is a number between 0 and 1. Hi, everyone. This is the last lecture, and we're here at the end of the semester. But looking at the clock, it says I'm at 39 minutes, so maybe I have 20 to 40 minutes left to finish the lecture. I won't take that long, but first, I just want to say I think you guys have done a pretty awesome job this semester. I think these circumstances have been extraordinarily difficult, and I'm kind of amazed by how everyone has kept up and took all their quizzes and their midterm, and now are going to take a final and actually learn exactly what students learn every year in this course. But in your case, given the circumstances, it's a lot more impressive. So the syllabus says this course ends with chapter 9, but in fact, there's kind of one core topic that we've left out, which is kind of cementing this idea that probabilities have something to do with relative frequencies. So we have about 15 more minutes here that I'd like to talk to you and explain this little tidbit from chapter 10 that'll kind of go full circle on our course to the first lecture when we said, well, probabilities are these abstract things. They're something that is a number between 0 and 1. Okay, so our final topic is the sample mean. So if you have an IID collection of random variables, x1 through xn, they have some common PDF, f sub x. The sample mean is what you traditionally call the average. You take the random variables and you add them up, and you divide by n the number of samples. So it's called the sample mean because it's the average of a collection of samples of the random variable x. It's important to remember this is not the same thing as the expected value e of x. E of x, right, is a property of the PDF, and it's a number, a constant. By contrast, this sample mean is a random variable. You take a collection of n random variables and you add them up and divide by n, you still have something random. So in order to keep it straight, we use a kind of a funny notation for this sample mean. We say it's capital N, the subscript n, which is to say how many terms are in there, that it's a sum of n things. And then we use an x to say, oh, it's samples of the random variable x. And remember, this quantity is a random variable, whereas this average, by averaging over the PDF, is just a constant. So whenever we introduce a new random variable, pretty much the first thing we do is we try to understand it by looking at its expected value and then its variance. So of course, this random variable, the sample mean, is the sum of NIID samples of random variable x. And assuming you're passing this course, you should know that this is, without doing these steps, that this is the sum of n expected values divided by n. And so it's exactly equal to the expected value ex of each sample. And second, you of course should know that the variance of the sample mean is the variance of these terms. But this constant here, 1 over n, is multiplying this random variable. So the variance is equal to 1 over n squared times the variance of x1 plus dot 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 xn. And you should also know that because these random variables are independent, the variance of the sum is the sum of the variances, and each has variance x. So it's n times the variance of x. And this reduces to variance of x divided by n. So fortunately, my steps here just simply re-derived what this theorem says. The expected value of the sample mean is the expected value, and the variance of the sample mean is the variance of each sample divided by n. And the important thing to think about here is that as n goes to infinity, as n gets large, the variance of the sample mean is going to 0 because variance of x, this numerator, is constant and n goes to infinity, so this term goes to 0. So there's only one random variable we know that has variance 0, and that's a constant. And so as n goes to infinity, if the variance is going to 0, it says in some way that the sample mean has to be converging to the expected value. So this first arrow, the variance is going to 0. This is just kind of baby calculus stuff. It's we have this expression, it's variance of x over n. It's equivalent to saying 1 over n goes to 0. The second arrow saying that the sample mean converges to the expected value, this is a little trickier because on the left side we have a random variable, and on the right side we have a constant. So somehow this random variable is becoming increasingly less random as n gets large. So this set of comments says exactly what I just said, and you can read it offline if somehow what I said on the previous slide wasn't convincing enough. So the sample mean converging to the expected value is what is called in probability speak the law of large numbers. There are different versions of the law of large numbers, but we'll consider the simplest one here. If we had a full lecture for this topic, I would go through the derivation of the next theorem, but since I promised this would be 15 minutes or less, we're going to skip the derivation and observe that in fact, the variance going to 0 says that the probability that the sample mean deviates from the expected value has to somehow be small and also go to 0. And the next theorem makes that clear. So the particular law of large numbers we'll look at is called the weak law of large numbers. And in this case, it's for having a finite number n of samples. The first version of the weak law, which is version A here, says that the probability that the sample mean mn of x differs from the expected value mu x, and it says that the absolute value of that difference is being greater than c, the probability of this event has to be less than or equal to the variance of x divided by nc squared. And you can take the second version of it says the same thing, but it describes a surer event. It says the probability that the sample mean differs from the expected value by the probability that it differs by some constant less than c has to be greater than or equal to 1 minus the variance over nc squared. They're exactly equivalent statements, but here's the thing. Um, C can be any arbitrary constant. For instance, we could have C equal to 10 to the minus 10. And so it says the probability that the sample mean differs from the expected value by some constant equal to 10 to the minus 10 is less than or equal to whatever the variance of x is, divided by n times 10 to the minus 20. Just to be clear, this is equal to 10 to the power 20 times the variance of x over n. And so, of course, this quantity on the left is a probability. And so this probability is always less than or equal to 1. And so this statement that this probability is less than this quantity here on the right-hand side is trivial when n is like, say, a billion or a trillion. It's still a very big number. However, when n can be arbitrarily large and when n is a lot bigger than 10 to the 20, this probability is going to 0. And so in fact, even for a very tiny constant like 10 to the minus 10, the limit of the probability that the sample mean minus the expected value is greater than or equal to 10 to the minus 10, right, is as n goes to infinity, this limit is equal to, I'm trying to erase this arrow, right, is equal to 0. In words, the probability that the sample mean differs from the true expected value by any tiny constant goes to 0 as the number of terms n in the sample mean goes to infinity. So what we just did is we showed the version of the weak law of large numbers for an infinite number of samples. This probability that we have some deviation by some constant c is going to be in the limit 0 as n goes to infinity. Or conversely, the probability that the sample mean and the true mean differ by some constant less than c, no matter how small c is, this probability is going to 1 as n goes to infinity. On the first day of lecture, we introduced the concept of probability models, and we kind of accepted or asserted that with a good model, the relative frequency of some event should be close to or maybe the same thing as the probability of that event. And now with this theorem, we can make this idea concrete in the following way. So let's consider n repeated trials of some experiment. And on trial I, we have a random variable xi, which is equal to 1 if event A occurs. A is some arbitrary event that we're interested in, and it's 0 otherwise. So in this case, the sample mean mn of x, x1 plus x2 up to xn over n, is equal to the number of times that event A occurs in the n trials divided by n. It's precisely equal to what we've called the relative frequency of event A. So, so what we're seeing is that the relative frequency, a concept that we sort of introduced on day one, is actually a particular kind of random variable derived from n repeated trials. And in fact, the sample mean of some indicator random variable for an event A is precisely the relative frequency of event A. Next, let's observe that because this xi is an indicator which is equal to 1 if event A occurs in 0 otherwise, it's just a Bernoulli trial that is calling event A occurring a success. And the consequence of this is that the expected value of xi is the success probability, which in fact is just P of A. So now when we examine the weak law of large numbers for this particular sample mean, right, we have that this sample mean is going to be converging to this expected value, which in fact is P of A. In short, the sample mean, which is the relative frequency, is some kind of an estimate of P of A, and it's a quantity that as n gets large is going to converge to P of A. So to be precise about this, let's give the sample mean a new name here. Let's call it P hat n of A. It's our estimate, our relative frequency of P of A based on n experiments in which we track the relative frequency of A. So with this terminology, our weak law of large numbers says the limit as n goes to infinity, the probability that the sample mean P hat n of A differs from the probability of A by any constant C is in the limit as n goes to infinity 0. So this is the result I promised you at the beginning of the course, that if we do enough trials, the relative frequency will converge to the probability. And in fact, from the weak law of large numbers, we just derived this simple theorem for the relative frequency converging to the true probability. And this is the main point I wanted to make, that was kind of the loose end that was floating around, and that I hope that the course would end in time, that I'd have a chance here in the last lecture to explain this. So we can finish by doing this simple quiz just to make sure we know what's going on. So we have x1 through xn are IID samples of the Bernoulli p equals 0.8 random variable. So this is kind of good exercise for the final exam. So the expected value of the expected value of a Bernoulli is p 0.8. Probably you should also know that the variance of x is p times 1 minus p, which is 0.8 times 0.2, which is 0.16, which is, of course, carefully chosen to have a nice square root. And the variance of M100 of x, 100 samples, if you remember the first theorem of this chapter, it's equal to 1 over 100 times the variance of x. So it's equal to 0.16 over 100. It's equal to 0.0016. So if you go back to the theorem for the weak law of large numbers, this quantity alpha is equal to the variance of x over nc squared, where this quantity is equal to c. So in fact, using the theorem, we have that alpha is equal to the variance of x, 0.16 divided by n, times 0.05 squared. Since n equals 100, this reduces to 16 over 24, which is 0.64. So it says that the probability, the sample mean of 100 samples differs from the true probability by more than 0.05. It's less than one, but even for 100 samples, it's a pretty significant probability. In this next part, we ask what's the probability the sample mean differs from the true expected value by more than zero point 0.1, and we'd like to make this probability to be less than 0.05, less than 5%. And to do that, we need to choose a large enough n. And the question is, how large does n need to be? So in this case, we have that 0.05 is equal to this alpha, and it's equal to variance of x over n and times c squared. C is equal to 0.01. It's this value here, right? And of course, variance of x is 0.16. So this is 0.16 over 0.01n. A little bit of calculation, and this says that n has to be 320. When an election pollster conducts a survey to find out what is the probability P that someone, a random voter, will vote for a particular candidate. They'll do a calculation very much like this and conclude typically that you'll maybe need something like n equal to 1100 voters in order to have the probability of this difference being sufficiently small, less than something like 5%. Typically, an article about polling in the newspaper will, in some paragraph, have a few words about this. So the past example, we found all we needed 320 samples, and in some ways that's an overestimate because the weak law of large numbers from which we got that result didn't make any assumptions about the distribution of the random variable x. So for instance, if you know that the xi's are Gaussian, then you can do an exact calculation of the probability of this deviation using the phi function, and you'll find that will tell you you need far fewer samples. So this homework problem explores this a little bit, and this is the kind of homework that is using, for instance, the central limit theorem. That's good stuff to do for the exam.